So in this next section, we're going to have a look at couples. So a couple is a moment that's generated by two forces. So we've got two forces. They've got the same magnitude. Their lines of action are parallel, but they're separated by a distance d. And so that's what's meant by a couple. So the easiest way to visualize that, if you're applying a couple to an object, so suppose I've got some kind of general object and we're applying a couple to that. So we're applying two forces opposite, maybe it's got a point of fixity over here somewhere, or we're just interested in finding the moment around that point. Then an easy way to think of that is it's as if you've stuck on one of these. So you've stuck on a hand wheel like so, and you're trying to rotate that hand wheel as this fella is in this picture here. So that's basically what a couple is, and that wheel is fixed to this body, and then we'll see what that couple would do to the body as we go on through this little presentation. Okay, so that's what a couple is. It's basically you're applying two equal forces in opposite directions that are parallel, the lines of action are parallel, and they're separated by a distance d. So we'll just call this one, let's just find a color that stands out. So force 1, force 2, they're equal and opposite. And let's just take a point in the middle here, A. Let's try and think about what this is doing. So if we think about all the conditions we have for static equilibrium, so we'd have the sum of all the x components must be equal to 0, the sum of all the y components must be equal to 0, and that would be enough. If these forces converge to a single point, we could use particle equilibrium, and these two conditions would be all we would need. But in this case, forces don't converge, so you need an additional criteria, and that's that sum of all the moments must also be 0. So let's have a look at these different criteria in the context of a couple. So we'll look at this one first. So in this case, the x component is aligned, the force is aligned with the x-axis. So if we took the usual axes, x horizontal, y vertical, then for the components of the forces in the x direction, we would just have sum, let's get the right pen color. So sum of the x components is equal to F1 plus F2, which would just be F1 is positive, F2 is negative, is 0. And that would actually be true for any of the forces, even for these forces here. If you were to add up, one more thing, the sum of the y components, we've got no y components, therefore sum of the y components is equal to 0. Now if you consider this one over here, we would have, let me just fast forward through this bit. I'm just going to draw on the x and y components and then I'll come back. And so we've got the x and y components. Because these are the same length and the same direction, this the y component of the force 1 must be opposite and the same magnitude as the y component of F2, so those two must cancel out. And similarly, the x component of F1 is equal but opposite to the x component of F2, therefore they'll also cancel out. So it's still true, even when the forces in that moment are at an angle, the sum of f of x is fx is going to be 0, and the sum of fy is also going to be 0. And so all your force components are always going to cancel out for these things. There's an even quicker way to think about that. If I just get rid of these, how do you add force vectors? Well, you put them nose to tail, put these nose to tail. This is going to come up here. You're going to be back to where you started. Remember, we had that rule as well when we're doing it graphically. Therefore, force components are always going to cancel out, so you're going to get no force component. But let's have a think about what happens with the moments. So the sum of the moments, let's take a point A. so about point A. So the sum of the moments about the centre of that hand wheel is going to be, so we've got the first moment from this force up here, we'll just call them M1 and M2, equals M1 plus M2, which equals, so for M1, we've got a force of 30 newtons and it's 0.2 meters from the centre, so the total distance across the wheel is 0.4, but this distance here is 0.2 meters. So we've got 30 times 0.2 and it's heading in a clockwise direction, so it's negative. So that's going to be negative 0.2 times, we should use F times D. Well, doesn't really matter, but I'll just keep it to F times D. So it's going to be 30 newtons times 0.2 meters. For this force down here, we've taken it to the centre, so the lever arm is the same. So it's still going to be 0.2 meter lever arm. The force is also the same. And in fact, the moment is in the same direction as well. So it's going to try and turn this wheel this way. And so you've still got a clockwise rotation. You've still got a negative moment. So it's also going to be minus 0.3 times 0.2. And so what I'm going to do is going to do one more step. It's minus 30 times 0.4. So you've got two of those, 2 times, it's not 0.3, sorry. It's 30 times 0.2. So you've got 2 of these, so it's the same as minus 30 times 0.4. Why am I writing that? Because that 0.4 is just the distance between the two forces. So it's just, which in our case would be minus 12 Newton meters. And that's generally the case. So the moment for a couple is equal to the magnitude of each force times D, where D is the distance between the forces. And so there's a place we have to be careful here. Sometimes when you look at a couple, you would think it would be 30 plus another 30, 60 times 0.4, but it's not. It's the magnitude of each force, of one of those forces, times the lever arm. Why is that? Well, if you imagine a point in the middle, the lever arm from that point is actually half of the total distance. Therefore, if we're calculating the moment, it's really this 30 times 0.2 plus another 30 times 0.2, which is just 30 times 0.4. So just be careful with that one. That's what a couple is. What happens when we apply those to a kind of general object? So if we apply a couple to an object, let's have a think about what happens. And there's some quite interesting results come out of that. Just move this up a bit. See if I can move this across. So we've got a kind of general object. We're applying a couple to this point here, and I've just chosen the point that's midway between those two lines. And so the way to think about that, just let me bring this to the front, is it's almost like you're attaching a hand wheel at this point, and then you're turning that hand wheel where the forces are shown. That hand wheel is like welded onto that object, and so it's welded here, and so you're applying those two forces. And so what would that do to the object? You can maybe see intuitively it's going to try and turn that object, but let's have a bit of a look at it and see what results we get. So all we already found, this is basically point A, we already found that if you choose a point in the middle, then the moment associated with those two forces is just F times D. We're going to do a couple of other points now. I'll call that one B, but I'm going to actually do another one, C, first. So this point here, C. I'm going to do that first and figure out the moment to there. Let me put in some numbers just to make it real. So we'll say that our lever arm, I'll draw it up here, the lever arm between the two we'll keep it as it was before. So that was 0.2 meters, I think. Let me just double check that. No, it was 0.4 meters. So 0.4 meters. And we'll do, the forces will be the same as before, 30 newtons for each force, 30 newtons. So previously we found that the lever arm, or the moment associated with this couple, was 30 times 0.4. Let's try C now and look at what the moments would be about the point C. And so the moment, moment about C is just going to be, so this force, its line of action aligns with C. You use this quite a lot when you're doing statics problems. You choose a point where one of the forces crosses that point. What does that mean? It means that the moment from that force is 0. We'll again call this F1 and F2. So we could say that the moment about C is equal to M1 plus M2, which is going to be, so M1 is just going to be, this is the perpendicular distance to that point, so that's the perpendicular distance to that point here. So it's just going to be 0.4 meters, and the force is 30. So that's, let's just write it out, F1 times D1 plus F2 times D2. As always, we need to be careful about the direction of these moments. So at the moment we're thinking about rotation about this point C. So this force with this lever arm is going to rotate clockwise around C. So it's going to try and rotate it this way. F2, it's going, the line of action goes through C, so as we discussed already, that's going to have 0 moment, so negative, positive, doesn't matter, it's 0. So this needs to be negative. And then we can calculate, so minus 30 times, distance 1 is 0.4, and so again we get minus 12 Newton meters. So previously we had the forces horizontally in opposite directions. We chose the point in the middle, we calculated the moment, we got minus 12 Newton meters. This time we've got the same forces, same distance, but they're vertical this time. Still get the same thing, 12 Newton meters. So it doesn't really matter which direction these forces that make up a couple are pointing. You're still going to get the same moment no matter what. And we're also finding that that moment doesn't change for different points. So the moment if you choose point A is the same as the moment as if you choose point C. Let's have a look at B now. We'll have a go at that one. So what I might do is just erase all this stuff just so we don't get confused about what's where. And so we just think about these two forces. If you were to combine those, what would be the moment around B? I might just rub off A as well. So I can't rub off the other one, it's on the drawing. But so what would we have to do? Well, we'd have to find the lever arm to those two forces. Oops. So the lever arm to the first force is the distance at right angles. And let's say that's 1.2 meters, say. And then we know that the distance between the two forces is 0.4 meters. We're not going to change that. The lever arm to point B from the second force would be along the same line. I'm just going to draw it to the side so that we can see it. And so that distance there would be 1.2 plus 1.2 plus 0.4, which is going to give us 1.6 meters for that one. Okay, so let's calculate the moment around B. So it is equal to, just keep this, we've got the same notation, M1 plus M2, which is equal to, so let's think about direction. So this is force 1 here, and so got B here, the force is going this way, clockwise, so that's negative. So negative F1 times D1. And this force, it's going this way around B,
So that's going to be anti-clockwise, so it's positive, plus F2D2, which is equal to minus 30 times 1.6 plus 30 times 1.2. You can do the algebra on that and you'll find that it's minus 30 times 0.4. So again, we're back to the same answer, minus 12 Newton meters. So it doesn't matter which point you take, you're always going to get that same answer. It's always going to be minus 12 Newton meters, and it's always going to be the case that these forces cancel out. So you're going to have no net force, you're just going to have a moment. So you're going to have, in this case, we've got y component, one up, one down. Those y components will cancel out, and the overall force will be 0. Let's just do one more. So what we've seen here is that no matter which point you take within this shape, or within this body, for a moment applied in this position, you always get the same result. It's always the case that the moment's minus 12 Newton meters. But these were a bit of a special case. We've always got them aligned with either the x or y axes. So we'll just do one more example just to show that this is always true. X and y components are always going to cancel out and your moment is always going to be the same. So what we'll do, let me just go back to my original drawing for this. So we will just take that couple and we're going to move it over here somewhere and we're going to rotate it around a little bit. Maybe it's over here. And we're going to take the same point B. We're not going to change the point B, but we're just going to move that couple from one location to another location. And then we'll repeat I'll work through the calculations and we'll show that we get the same answer again. So what I might do is just fast forward that, and then I'll meet you on the other side of the fast forward.
So I've found, so we've got our two forces that make up the couple. I've found the lever arms to those two forces. So one of them to the F3, what I've called F3 is 0.5 to the other one's 0.9. And then I've calculated the moments and shown that again we get the same answer. And it's because essentially you end up saying the longer lever arm, take away the shorter lever arm, is always going to leave you with this lever arm of 0.4. So you always end up with the same answer. So just to summarize, a couple is two forces that have parallel lines of action but opposite directions. So a couple is something like this. And got a lever arm between them. Where's that? 47. So this must be 3. Lever arm between them of D. Suppose this is F and this is F, and we'll just put a dot in the middle just to show where we're applying it to. If you've got some general shape and you look at the moment of that couple about the point A, then the moment about A is equal to the force, so the magnitude of one of the forces times the distance, or the magnitude of either of the forces, they both got the same magnitude. And we also know that it doesn't matter what point you choose in this body that you're applying the couple to. If you calculate the moment, you'll get the same answer. So probably easier to write this as the moment at A is equal to the moment at B is equal to the moment at C. How far did I go? Equals the moment at D. which equals the force times the lever arm. And remember, it's just the force of one of these. Now, what we can also say, it's pretty much the same concept, just a different way of thinking about it. So we've got the same body. Let's just leave one of these points of rotation that we're considering. Should have left that one. Get rid of those ones. We also know that it doesn't matter where you apply that couple within this body. The moment at A or at any other point within that body, the moment at A is the same. So we could apply this couple over here. We could apply it over here. It wouldn't matter. You'd still get the moment at A is equal to F times D. Excuse me. So moment at A or any other point in the body is equal to the magnitude of one of the forces times the lever arm. And we just have to be careful about that we're not adding up these forces in times of the lever arm. It's just one of these forces times the lever arm. Not only that, but if you were to rotate this couple, it would still be true. Or if you were to rotate the forces, rather, it would still be true. So if the forces have the same magnitude, but they're at a different angle, there is something we have to be careful about. So I'm just going to draw roughly, try and get those the same length and the same distance apart. Now there is one place we need to be careful here. We need to make sure that the direction of the rotation of the couple doesn't change. So in this case, you've got a couple going this way, a couple going this way. If you think about this point in the center, that's rotating clockwise. So I need to make sure that the same thing happens for these ones. So that also needs to go clockwise. So it's like that. It's the same force. It's the same distance between. And then you'll still get the same moment. Okay. And in this case, all these moments will be negative. They're all going clockwise. So that's that. We'll just do one more thing I want to show you about couples, and then we are done. We can do some examples. So I just need to grab a diagram from that, and then I'll come back again. So this last point I want to look at, I can illustrate it with this diagram. So here I've got three different couples. What we'll do is we'll imagine that these are being applied to some object, and we'll calculate the moment associated with them. So you don't really need to worry about where the point in that object is. That's what we've just been talking about. You can just say that the moment is always going to be the force times the distance between the forces. So let's just do that. So say this first one. So force for this one is going to, moment for this one is going to be force times the lever arm, which is equal to 4 times 1, which is equal to 4 newtons, meters, and this time we've got an anti-clockwise rotation, so it's positive. Let me just move this up a little bit, and I might just get rid of this. So I'm not cluttering, that's where I copied it from down here. Now, what we've done for this next couple is we've halved the force, but we've doubled the lever arm, and you can probably guess already what's going to happen. Moment equals force times distance between the forces, which equals 2 times 2, which is 4 Newton meters, and we're still going anti-clockwise. That's why we had to be careful about the rotation. If you do those arrows the other way around, you're going to get a negative. Last one, compared to the first one, we've quartered the force. We've quadrupled the lever arm. So again, your moment is going to be force times distance, which is equal to 4 times 1, which is going to be 4 Newton meters again. And so when you apply a couple to an object, all that really matters, So the forces always cancel out, so you get no net force. So your Fx component and your Fy components always add up to 0 because you've got two opposing forces. So the only thing it puts in there is a moment. So really the only thing that matters about a couple is this moment. The force doesn't really matter. And so you could draw the same couple, or you could certainly draw a couple that gives you the same moment, but you could draw it an infinite number of different ways. You could draw it any way you want. You just have to make sure that whatever force you choose, you select a distance between those forces so that F times d stays the same. And it's for that reason we sometimes draw a couple as a dot to show the point of application, and then we just show the direction that the moment is trying to rotate the object, and then write down the moment 4 Newton meters. And so this couple here, if we write it this way, we could draw that as any of these. They all give you that 4 Newton meters. And so often we'll just do a shorthand and we'll just say, look, we've got a couple and it's going to give rise to a moment of 4 Newton meters. Okay, so that's it. So now we'll move on and do some examples that involve couples.